Hello everyone. In today's recorded session, we'll be sharing a small video on the derivation of series RC circuit. The question might be like this: derive an expression for a series RC circuit and obtain the instantaneous value of voltage, current, and power, and write down the capacitive reactance equation, or show that in an AC circuit, in a series AC circuit, current leads the voltage by an angle phi, and derive certain expressions relating to it. So this might be the question which will be asked. Let me share my screen right now. Yes, it's a derivation which is related to series RC circuit. Series RC circuit. Okay, series RC circuit. So this is R, this is C. Okay, so it is related to series RC circuit. It is having an AC voltage V, which will be equal to Vm sine omega t. This is the resistance R, this is the capacitance C, and this is the value of the current which is flowing in the circuit. Now, in a series RC circuit, in a series RC circuit, in a series RC circuit, we have current, current which is leading, current which is leading by an angle phi. So where phi is called the phase angle, where phi is called the phase angle in degrees or radians, in degrees or radians. V will be equal to Vm sine omega t. That is the applied AC voltage. So consider an AC circuit where R and C are connected in series, where R and C are connected in series, and R is the resistance, R is the resistance in ohm, and C is the capacitance, C is the capacitance in farads, okay, farad. Okay, so now I have this series circuit where R and C are connected in series. It's a pure resistance and a pure capacitance. Once it is connected in series, it forms a series RC circuit. So in the series RC circuit, I can have the relation between the instantaneous value of current, that would be equal to Im sine omega t plus phi. Then V would be equal to Vm sine omega t. So this is the applied AC voltage. This one is the instantaneous value of the current. Okay. Now, if I want to talk about the vector diagram, okay, if I want to talk about the vector diagram, okay, so how shall I write it? So V and I are the RMS values of, are the RMS values of voltage and current, values of voltage and current. Okay, now if I want to write the vector diagram, I'll take current as the reference axis, current as the reference axis, and VR is the voltage, VR is the voltage across the capacitor. VR is the voltage across the voltage across the resistor. Sorry, it is voltage across the resistor. Next, this is VR. Now, current and voltage. So, in a pure capacitive circuit, in a pure capacitive circuit, voltage voltage lags voltage lags current, voltage lags current by an angle of by an angle of pi by 2, pi by 2 or 90 degrees, pi by 2 or 90 degrees. So how it would be? It would be like this. So this is minus Vc. Okay, so minus Vc. Why it is called as minus Vc? Because V would be equal to Vr minus J into Vc. So the rotation would be J cube. J cube is minus J. That's the reason why I can express it like this. So V would be equal to Vr minus J into Vc. Okay, so I can write it like this. This is the expression for the resultant voltage, that is V, that is the applied RMS voltage. So V is the applied RMS voltage. V is the applied RMS voltage. V is the applied RMS voltage. So this is the angle of phi. Okay, this is the angle phi that is created. Okay, so this is the angle phi, and what you can see here is current is leading. Okay, current is leading. Current is leading by an angle of by an angle of phi by an angle of phi in a series RC circuit. Series RC circuit. So series RC circuit is an example of certain filters where it is generally used to minimize any ripple content which is present there. Okay. So in such circuits, you will be having the current leading by an angle of phi that is applicable only in a series RC circuit. Okay. So now VR is the voltage drop. VR is the voltage drop across resistor R. Across resistor R. Okay. VC, it is VC will be the voltage drop across the capacitor C. Across the capacitor C. So VR can be written as VR can be written as I into R. Okay, VR can be written as I into R. VC can be written as I into XC, where XC will be the capacitive reactance. XC will be the capacitive reactance in ohms. Capacitive reactance in ohm. Okay, so XC will be equal to 1 divided by omega into C. XC will be 1 divided by 2 pi f into C, where XC is related to the capacitance. Okay, so if the capacitance is increased, the Xc, which is the capacitive reactance, decreases. So VR would be I, that would be equal to VR divided by R. Okay, so I, you can calculate the value of current I. Okay, so you can have R. Okay, like this. Okay, so you can calculate the value of current once you know VR. Once you know VR and once you know R, I can be calculated easily. Okay, but in general, if I want to talk, so how can I write the current I? Okay, so V that would be equal to I into Z. Okay, V that would be equal to I into Z for an AC circuit. For an AC circuit, V would be equal to I into Z, where Z would be equal to R minus JXC. R minus JXC. Okay, so Z would be equal to R minus JXC. So mod Z, that would be equal to root of R squared plus XC squared. R squared plus XC squared. The angle Z would be tan inverse of, okay, XC divided by R with a negative sign again. So that is XC divided by R. Tan C would be XC divided by R. So minus, okay, so this would be a minus again. So tan inverse minus. Okay, so when the minus sign indicates, it is the angle which is already there. So you can have tan inverse of minus XC divided by R. So you can see that in the numerical problem also how we are going to solve it. Okay, so if I take Z to be equal to R plus J times minus XC, okay, so tan inverse B by A, so that would be minus XC divided by R as the angle. So I, okay, so that is given by V divided by Z. So I will be the RMS value of the current. V is nothing, also V is nothing, V and I are the RMS values of the voltage and current. RMS values of voltage, voltage and current. Okay, RMS values of voltage and current. So for an AC circuit, V would be equal to I into Z, where Z, which is the impedance offered, impedance offered, impedance offered by an AC circuit, by an AC circuit, impedance offered by an AC circuit. Okay, so now I can have this impedance relation. Okay, so I'll be having I, which will be equal to Im sine omega t plus phi. Okay, then V would be equal to Vm sine omega t. So this is equation 1. Okay, so this would be equation 2. Current leads the voltage, current leads the voltage, current leads the voltage by an angle phi, by an angle phi. Okay, current leads the voltage by an angle phi. Okay, so V would be equal to Vm sine omega t. So Z, okay, so important points to remember, Z would be equal to R minus jXc. So Z will be root of R squared plus XC squared. Okay, so R squared plus XC squared, so which is nothing but the modulus of mod Z, that is nothing but the magnitude, which is given as root of R squared plus XC squared. So the angle at which mod Z can be measured, that is tan inverse of minus XC divided by R, tan inverse of minus XC divided by R, that is minus tan inverse of XC divided by R. Okay, so that is minus tan inverse of XC divided by R. Okay, so that's how the angle is present there. Okay, so you can write the instantaneous value of the voltage and also the value of the current clearly. Okay, so now the impedance triangle would look like this. Impedance triangle, impedance triangle, impedance triangle. Okay, so I can have R, this is XC, R, this is XC, and this is Z. This is minus here, so this is the angle phi. Okay, this is Z for an AC series RC circuit, series RC circuit. Okay, so this is the impedance triangle. So what I can leave you is, okay, self study, which is a self study topic. Sketch the waveforms, sketch the waveforms of instantaneous value, instantaneous value of voltage and current, voltage and current. Okay, voltage, instantaneous value of voltage and current, and power, voltage, current and power. Okay, so the average power, the average power P, that is given by V into I cos phi, V into I cos phi. P will be equal to V into I cos phi. So this is the impedance triangle that is formed, and the average power in a series RC circuit as well as RL circuit or RLC circuit. So the average power would be P would be equal to V into I cos phi. So where V and I are the RMS values, and cosine of the phase angle is the power factor. Cos phi is the power factor. Cos phi is the power factor. Okay, so which is always leading in nature. It's always leading in nature. It's always leading in nature. So remember, in a series RC circuit, in a series, in a series RC circuit, in a series RC circuit, the power factor will always be will always always be leading okay. So cos phi, okay, cos phi will always be having a value which is leading, just leading. Okay, so this is what you can remember. Okay, so P would be equal to V into I, cos phi. Next, what you will do, I would be equal to V divided by Z, where Z would be root of R squared plus XC squared. Okay, next, uh, tan phi, okay, tan phi would be, okay, tan phi would be XC divided by R. So with the minus sign, if you can take it, phi would be equal to minus a tan inverse of XC divided by R. Okay, so if you are going to take the angle, okay, that is having with respect to the impedance, so that is negative. And once you are having the angle there, so if you want to write it in the instantaneous value, I can write it as Im sine of omega t plus phi. Okay, so that's how I can write the instantaneous value of the current. So this phi is related here, so that's how minus phi would be that, minus of minus phi, that is will be equal to plus phi. Okay, so that is the instantaneous value of the current. Okay, so we will stop here. In the next video, I'll be sharing you the numerical problems related to the series RC circuit and few problems related to series RL circuit. Okay, so thank you everyone.